Alright, let's take a look at integration. Again, a couple different ways of saying integration. First one, antiderivative. The second one is indefinite integral. They all refer to the same notion. Alright, this particular section, 5.4, we're going to take a look at fundamental theorem of calculus. And fundamental theorem of calculus is used to evaluate the area under the curve. This particular section, we're gonna take a look at evaluate the definite integral using the fundamental theorem of calculus, and we're gonna learn the mean value theorem of integrals, and we'll take also as well as the average value of a function over a closed interval, something like square bracket a comma b, and we're going to try to understand the second fundamental theorem of calculus, and then learn the net change theorem. Alright, so fundamental theorem of calculus, it's used for evaluate or find the area under the curve. And two major branches of calculus was developed: differential calculus and the integral calculus by two famous mathematicians, Isaac Newton and Gottfried Leibniz. And the biggest similarity between the theorems they discovered is called fundamental theorem of calculus. They look at it from different point of view, but there's an intrinsic connection between those two discoveries. Alright, so let's take a look at the comparison between the differentiation and definite integration. So for differentiation, we estimate the slope of tangent line using delta y over delta x. Okay. And slope of tangent line was developed from the slope of secant line. Okay. And when we talk about integration, in the previous two sections, we look at the area of rectangles, estimate the area under the curve using a rectangle. So area equals to delta y, which is the height, and delta x, which is the base. And under the fundamental theorem of calculus, area of the region under the curve was calculated using delta y times delta x approximately, because differentiation and integration has an inverse relationship, meaning it's like multiplication and division. They are inverse operations. Okay, so slope of tangent line was defined using the quotient delta y of delta x. The area of the region under the curve was defined by the product delta y times delta x. And the fundamental theorem of calculus states that the limit process preserves the inverse relationships between the integration and the differentiation. Alright, so let's take a look at the first fundamental theorem of calculus. This is the first one. We're going to take a look at the second one in a bit. If a function lowercase f of x is continuous on a closed interval, square bracket a comma b, and f is antiderivative of f on the interval a comma b, then integral f of x with respect to x from x equal to a to x equal to b equal to uppercase f of b minus uppercase f of a. So this thing basically works like this. Based on the description, uppercase f of x is an antiderivative of f on the interval a comma b, so that means it's going to be f of x plus c, and given definite integral, so x is from a to b. So now what we're going to do is replace x with b first, so plugging b into the function, so we get f of b plus c. That's first. And also you plug in a into the function, so you get f of a plus c. And now just expand it. You're going to see f of b plus c minus f of a minus c. As you can see, c was cancelled, and you end up with f of b minus f of a. And that's how they come up with this fundamental theorem of calculus. And the standard procedure to find the area under the curve, first of all, find the antiderivative of f of x. And we use a standard notion. For example, let's say we want to do x squared dx. This is standard notation for using the fundamental theorem of calculus. So first of all, find the antiderivative, and right here we're going to use the general power rule, adding 1 to the exponent, and the new exponent becomes the denominator. Then we omit c. Eventually we're going to cancel c, right? I'll just show you the previous slide. So this is from 2 to the 4. So it's basically x cubed over 3 to the 4. Now we're going to plug in 4 first. We get 4 cubed over 3 minus 2 cubed over 3. 4 cubed is 64 over 3, and 2 cubed is 8 over 3. 64 minus 8 is 56 over 3. So the answer turned out to be 56 over 3. So that's area under the curve. So if you look at it from a graphical point of view, the graph look like this. This is function f of x equal to x squared. It's a parabola concaving upward, passing through the origin. So we're looking at 1, 2, 3, 4. Right? Looking for area from 2 to 4. Alright, so basically we're looking at this area under function f of x equal to x squared, and this area is equal to 56 over 3. Okay. And any area above x-axis, this is x-axis, is positive. If this area is under x-axis or below x-axis, then area is going to be negative. So that's a unique feature about the area under the curve. Okay. Let's take a look at some examples. Okay, let's take a look at first one. And definitely integral for function x squared minus 3 dx from 1 to 2. Okay, so first of all, find antiderivatives using the power rule. So x squared, you apply the power rule, then 2 plus 1 over 2 plus 1. And for antiderivative of 3 becomes 3x. Any constant becomes linear term. Right? Then multiply by x. It's from 1 to 2. Now plug in, simplify first. X cubed minus 3. X cubed over 3 minus 3x. 1, 2. Now plug in both numbers. Plug in 2 first. So 2 cubed over 3 minus 3 times 2 minus 1 cubed over 3 minus 3 times 1. So that becomes a over 3 minus 6 minus 1 over 3 minus 3. Expand it, we end up with a over 3 minus 6 minus 1/3 plus 3. Simplify that. Combine a over 3 by 1 minus 3 and becomes 7 over 3. And subtract it. Minus 6 plus 3 minus 3. 7 over 3 minus 9 over 3. That turned out to be negative 2 over 3. You probably wonder why the answer is negative 2/3. So let's draw the graph and you'll be able to understand why this is negative. Okay. X or Y. Negative 1, negative 2, negative 3. So this is a graph of the power. And this, as you can see, we're looking at from 1 to 2. So this is 1, 2. So looking at this narrow area right here, and since it's underneath x-axis, that means this area is going to be negative. That's why I end up with negative 2/3 as the area under the curve. Okay, so anytime you see the area under the curve is below the x-axis, the area must be negative. Alright, let's take a look at the second example. So right here you divide it a little bit, becomes 3, square root of x becomes x to the half. Now apply the power rule. So 3 times x, half plus 1 over half plus 1. That's from 1 to 4. So now simplify the rational expression first. 3 over 2 or 3 over 2. Half plus 1 is 3 over 2. And let's just turn this quotient as a multiplication. So we got 3 times 2 over 3. And cancel 3. We end up with 2x 3 over 2 So first of all, plug in 4, so you get 2 times 4 to the raised to 3 over 2 power. And plug in 1. So 2 times 4 cubed, square root of 4 cubed. That's how you turn the exponent into the minus 2 times 1. And 4 cubed is 64. So square root of 64. Square root of 64 is 8. 2 times 8 minus 2. That's going to be 16 minus 2. That becomes 14. So area under the curve for this function is 14. And let's take a look at the third one. Antiderivative of secant x squared becomes tangent x. Nice and simple. 0 power 4. Now just plug in power 4 first, we get tangent over 4 minus plug in 0, we get tangent 0. So tangent pi over 4, tangent 45 degrees is equal to 1. Tangent 0 becomes 0. 1 minus 0 give you 1. Okay, so the answer is area under the curve for secant x squared for x from 0 to pi over 4 is equal to 1. Okay. And just the detailed solutions we'll go over. And next, let's take a look at the mean value theorem for integrals. You'll probably also see the abbreviation for mean value theorem as m dot t. Okay, so basically, the area of a region under the curve is greater than the area of the inscribed rectangle and less than the area of the circumscribed rectangle. The mean value theorem for integral states that somewhere between the inscribed and the circumscribed rectangle, there's a rectangle whose area is precisely equal to the area of the region under the curve. So how this thing works is basically you carefully finding the point C where since we're trying to find the area under the curve here, including this, and if you locate the C properly, you'll be able to locate the area which is going to be this area is going to be equal to that area. So that will make that this rectangle area will be the same area as the area under the actual curve. So for the rectangle area, it's very easy to find area. It's going to be height times base. The base is b minus a. The height is f of c. So the area is going to be equal to f of c times b minus a, which is equal to area under the curve using fundamental theorem of calculus. Okay, so that's how using mean value theorem of integrals to find the area under the curve using a rectangle. Alright, so let's take a look at the mean value theorem for integrals. If f of x is continuous on a closed interval a comma b, then there exists a number c the closed interval a comma b such that definite integral f of x dx from a to b equals f of c. This is area under the curve. This f of c's height, b minus a, is the base of the rectangle. And the rectangle has the same area as the area under the curve. And another application, important application, is average value of the function. And it's defined like this: f of c in the mean value theorem for integral is called the average value of f of x on a closed interval a comma b. So if f of x is integratable, that means antiderivative exists. On a closed interval a comma b, then the average value of function f of x on the same interval is 1 over b minus a times and definite integral of f of x with respect to x from a to b. Okay, and that's how you compute the average value of f on an interval. And let's take a look at an example, right? Find the average value of f of x equal to 3x squared minus 2x on the interval 1, 4. Alright, so let's write down the formula. So in this case, a equal to 1, b equal to 4, f of x is given. So let's plug in all of that. Just 1 over 4 minus 1 times 1, 4. F of x is 3x squared minus 2x dx. So simplify the coefficient, it becomes 1/3. And let's apply the power rule here. Apply the power rule on the second one as well. By default, that's invisible 1 for in the second term as exponent. This is from 1 to 4. Now it becomes 1/3. 3x cubed over 3 minus 2x squared over 2. Let's simplify, cancel 3 on the first term, cancel 2 on the second term. So end up with 1/3 x cubed minus 1/3 x squared on 1 to 4. Now plug in 4 first, we get a 1/3. So 4 cubed over 3 minus 4 squared over 3. And plug in 1. 1 cubed over 3 minus 1 squared over 3. Four cubed is 64 over 3 minus 4 squared 16 over 3 minus 1/3 minus 1/3. This get cancelled. 64 minus 16, that's 48. Since they are like terms, 48 over 3. 48 over 3 becomes 16. So the average value of f of x equals 3x squared minus 2x is going to be 16. You can look at the detailed solutions on average values right there. Okay. Now let's get to the second fundamental theorem of calculus. It's also second fundamental theorem of calculus also used to evaluate area under the curve. From different point of view, right? Okay. So let's take a look at a comparison between the two different fundamental theorems of calculus. This is the first one, and this is the second one. For the first one, if you look at the definite integral itself, both lower limit and the upper limit is a constant. Right? Both a and b are constant. F of x is a function of x, and with respect to x, when we do the definite integral. And for the second fundamental theorem of calculus, lower limit is constant, but upper limit is x, and uppercase f of x is a function of x. Now looking at function expressed in terms of t, so lowercase f of x is a function of t with respect to time t. Okay, and that's a major difference between two fundamental theorems of calculus. Alright, so let's take a look at evaluate a function f of x equal to cosine t dt, and t is from 0 to x. So f of x so antiderivative of cosine t becomes sine t. Okay. And now plugging x, you get sine x. Plugging 0, you get 0, sine 0, sine 0 is 0, so it becomes sine x minus 0, so just sine x. Okay. And first one, when x equal to 0, and then f of 0 equals to sine 0, which is 0, because eventually you know that right here f of x equal to sine x. So that means area under the curve from 0 to 0 is equal to 0. Second one, when x equal to pi over 6, f of pi over 6 equals sine pi over 6. Pi over 6 is 30 degrees, sine 30 degrees half. And that means our area under the curve from 0 to pi over 6 for function sine of x is equal to half. So when x equal to pi over 4, so f of pi over 4 equals sine pi over 4. Sine pi over 4 equals radical 2 over 2. Fourth one, x equal to pi over 3, so f of pi over 3, sine pi over 3, sine 60 degree equals to radical 3 over 2. So the area on the curve from 0 to pi over 3 equal to radical 3 over 2. X equal to pi over 2, f of pi over 2 equals sine pi over 2. Sine pi over 2 equals sine 90 degrees, which is 1. Okay, so the next page is a summary of the area under the curve. As you can see, second fundamental theorem of calculus also measures area Okay. As a summary, how those areas are calculated. So in this case, using the second fundamental theorem of calculus, an integral was used as an accumulation function, okay, to generate the area under the curve. So we're accumulating area under the curve for f of t equals cosine t from t equals 0 to t equal to x. So basically, let's take a look at the second fundamental theorem of calculus. So if f of x is continuous on an open interval I containing a, then for every x in the interval, when you're taking the derivative of definite integral f of t dt from a to x, that becomes f of x. Okay. Just basically replace, because derivative and the antiderivative cancel each other, right? And replace t with x, and you end up with the final answer. Okay, so let's take a look at this example. We find the derivative of definite integral of radical t squared plus 1 with respect to tan t from 0 to x. So as you can see, all you need to do is derivative, antiderivative cancel, and you just replace t with x. So it becomes radical x squared plus 1. Just that simple. Okay, so that's final answer using a second fundamental theorem of calculus. And the very last topic is net change theorem. The fundamental theorem of calculus states that if f is continuous on a closed interval a comma b, and then uppercase f of x is antiderivative of f from closed interval a comma b, then from the first fundamental theorem of calculus, definite integral of f of x with respect to x from a to b equals f of b minus f of a, because f prime of x equal to uppercase f prime of x equal to f lowercase f of x. And you could also, since f of x lowercase f of x equals f prime of x, so you can just change this to f prime of x. So end up with the same answer. And this is how net change theorem was developed. Okay, so definitely integral of the rate of change of quantity f prime of x gives the total change, net change, is that in that quantity on interval a comma b. So definite integral of uppercase f prime of x with respect to x from a to b is equal to f of b minus f of a. Let's say a chemical flows into a storage tank at the rate of 180 plus 3t liters per minute, where t is greater or equal to 0, less or equal to 60. Find the amount of chemical that flows into the tank during the first 20 minutes. Remember that net change theorem is based on the time t, so first 20 minutes meaning from 0 to 20. And the function is 180 plus 3t, and this is with respect to time t. Okay, so basically you just have to find an antiderivative of 180 plus 3t dt. This is rate of change. In order to find out the actual amount of change, you do the antiderivative or definite integral. So derivative of 180, antiderivative of 180 with respect to time t is going to be 180t. Antiderivative of 3t, we'll apply the general power rule. 1020. So it's going to be 180t plus 3t squared over 2 from 0 to 20. Now plugging 20 first, we get a 180 times 20 plus 3 times 20 squared over 2 minus, and plugging 0, we got 180 times 0 plus 3 times 0 squared over 2. So they both become 0. So end up with 3600 plus 20 squared is 400. 400 times 3, that's 1200 over 2. So it's 3600 plus 600, which is 4200. And this is definitely liters, right? So using the net change theorem, the amount of chemical that flows into a tank during the first 20 minutes will be 4200 liters.